Hello and welcome to our 10th topic in AI Topics, a series I've been doing for a little while now. It's interesting that it's this high up in the sequence because learning from examples is probably one of the most important things we do in the field of AI today. It is how you what you expect a intelligent algorithm to do is be shown some things and then figure out something from it. That's kind of the idea. So there's uh, lots of different forms of learning. So we'll start off by that of exposing kind of what is the context, what does it mean to learn, and if you're in an unknown environment, then it's essential. You need to know how to learn. Um, so that's basically you have to explore your environment to know what is available to you, be it resource wise or whatever it might be. It's also something that we do uh, to as part of construction of things, right? So sometimes you might expose an agent to reality rather than trying to write it down. So the basic idea though is that you're wanting to have the agent be able to do that bit that we've talked about of getting information from its environment and making changes or learning from that information to meet some goal, right, for some performance reason. There's several different kinds of learning. These are the most commonly ones you'll see, but there are some other ones that are kind of interesting as well. Supervised, you know the answer. It's that simple. You've got a labeled data set. One of those columns inside of the data set or more is the answer, so the outcome. And so given the other columns, you've got essentially the known outcome that is expected, and then you attempt to predict it using the various mechanisms to do so. Unsupervised, you don't know the answer. That's whenever we do things that are oftentimes in the world of clustering. Um, you could also potentially throw in some of the large language model stuff we're doing as well, because it's clearly not a labeled data set. So it maybe could fall into reinforcement, but probably not. Reinforcement is I don't know the answer, but I know how to rate how things went. So outcomes. So I have some function that I can call that allows me to evaluate if one approach is better than another. When we deal with learning agents, we've talked about this before. You've got essentially an environment with sensors and some sort of actuator or effector that does things to that environment. That environment may be physical or it may be virtual. You have some means of evaluating how well you're doing. You have some way of basically creating the model of the problem. So a problem generator, and then you also have some elements where you've got goals, and you may even have some planning going on as well. And then you may have some mechanism that is there to assess how well it is doing. So the critic to determine how well you're doing. Um, so whenever we talk about learning, you need to figure out kind of it's going to be driven by what type of performance element is used, which functional component is to be learned, and how that functional component is represented, and then what kind of feedback is going to be available. So here's some examples of some scenarios. Alpha beta search, you've got an evaluation function, you got a weighted linear function, perhaps as the representation, and then you have some outcome, a win or a loss, so the feedback. Um, and then you may have some other, so a logical agent, it's likely going to have some sort of transition model, or it could have, and the representation could be successor state axioms, and then you're looking for an outcome. So these are basically kind of ways of formally thinking about the components that go into a solution that's attempting to learn something. And then it is how do you evaluate which is which, right? So supervised learning, this is the one that's been around for quite some time. You use labeled data set. So you have this idea of a training set. This is data that you know the outcomes to, and you're going to do special stuff with it as you go through. So you're likely going to take your training set, and the labeled elements that you have separated into various other subgroups. Use one of those groups at the very last to evaluate how well you're doing. So you're going to have a test set that's pulled out of that training set to essentially try to determine how well the solution is generalizing, how well it's solving problems it hasn't seen before. The ground truth is the true answer. It should be in a test set. And again, the ground truth may also be coming about because of a segregation of a labeled data set. And it generally involves some sort of data exploration analysis where you've got to go learn about the data. That's going to be true of almost any kind of analytics you do. You've got to go poke around and see what's going on inside of the data. You have a best fit function, something that fits the data, but maybe not too well. And then, because if you do too well, then it doesn't generalize. And generalize is the ability to predict outcome on data that we haven't seen before during the training process. Underfitting, you didn't train it enough, so you're going to miss the patterns that you should find as part of the kind of generalization. Overfitting, you've looked too much at the data that you have so that you're doing really well on it, but not so well on patterns that you haven't seen before. So you've lost the ability to generalize. We talk about an inductive learning method. You basically come up with, you construct, adjust some sort of hypothesis to agree with F on some training set. And H is consistent if it agrees with F for all examples. And we've had these sort of discussions before of nomenclature. Example is curve fitting, and Occam's razor maximize a combination of consistency and simplicity. So rather than trying to come up with an overly complex way of trying to fit it, go with the simplest one. It will likely do best on things it hasn't seen before. Now, it may not do as well if there's some sort of natural skew, but that's a different problem. Decision trees. So learning a decision tree, and this is basically where you're going to take some data and try to figure out based upon some sort of hypothesis of how you should construct your tree. The expressiveness, decision trees can express any function of the input attributes. So Boolean functions, truth table rows, and so on, paths to a leaf. So it's a really relatively strong way of representing things. It's also very understandable for humans. And we generally prefer to find a more compact decision tree. So that means less layers. Hypothesis space is how many distinct decision trees within Boolean attributes and the number of Boolean functions. And it's also equal to the number of distinct truth tables with 2 to the n rows. So 2 to raise to 2 to the n. And so I'm going to go ahead and skip through some of this because it's a little off of what we're really interested in. Decision tree learning is your aim is to try to find a small tree that's consistent with the training examples. So back to the nomenclature, there's no examples that don't pass. So it's all of the things are trained well. And you want it to be small so that it doesn't have more layers than another solution that delivers as good of results. And to some extent, I've kind of also right then just did a little bit of model selection, right? I gave a bias towards a simpler model. And so that's one way that we might choose our models is around execution time, simplicity. And then once you've selected a model, you may end up having to do various forms of optimizations to it. So an error rate is the ratio to how often we get it right. So how many are right compared to how many are wrong. And there's a way that we use this label data set that I kind of alluded to. You have a training data set. That's the training you actually expose to the model with the intent of it adjusting its weights and attempting to fit it. A validation set is something you use that helps you pick the right model. So maybe you will use that data as part of an assessment step of the training process. It may be that if you're doing some sort of deep learning, you're running an epoch through, so epoch, basically all the fancy word of meaning that you've shown it all the data. At the end of that, each one of those runs through the data. You will likely use your validation set as a way of assessing how well you're doing, maybe determine loss functions and various other things. And then the test set is held out for to measure performance. And it's again held back from that whole set, and it's not been seen previously. Hyperparameter, those are basically the knobs that you can turn, so you can adjust and tune how the model does, maybe the number of Ks if you're doing K nearest neighbor and so on. It's a parameter, but it's not a certain model. So parameters of model classes, right? And it's used to optimize the process. And there is a loss function, which is you generally try to minimize rather than maximizing utility. So you try not to make mistakes rather than get the best overall outcome, which may be counterintuitive. Population-based training. This is training models in parallel. You choose the best, try again. Essentially, genetic programming, very similar to what you'll see inside of things like Azure ML or ML, AutoML. Talk about the theory of learning. Some concepts, computational learning theory. It applies to mathematical methods of learning systems. Probably approximately correct. So PAC, after enough testing, something not proven to be wrong isn't seriously wrong is the theory. So it's likely you can't prove it wrong, so it's probably okay. And some links if you really want to drill into these concepts. Linear regression and classification. The basic idea is that you're trying to fit something. So in the case of linear, you're fitting a line or something that is essentially not more interesting, so not a higher number of operations going on. You may have univariate linear regression trying to find a straight line that's going to fit some points, and that's what you see there on A. And then you may have a gradient descent that involves, it's kind of the inverse of hill climbing. You're looking to minimize loss, right? So you're trying to find the lowest point, if you will, in that graph. Linear classifiers, the idea is to be able to separate things with a line. So to take two things, split them into, or two sets of things and separate them, ideally with no error. And understanding that sometimes there will be error. Also, sometimes you'll take into consideration that that divider may have a length. So if you think about linear classifiers, you have an inputs or feature values. Each feature has weight, and then the sum of them is the activation, and that's what we do inside of a neural network, generally speaking. So looking at it, how it works, and this is very similar to expressions we've seen before. It's the adding up, so the summation of all of the weights times the feature's value. And then taking that and essentially determine at some point if it's going to be greater than some activation amount. And if it does, then it's going to activate. Logistic regression, similar to linear, except you're not necessarily dealing with a straight line. So you can have more interesting functions going on. In particular, you got things like that sigmoid function where it's not on or off, but of varying states between. And so a very powerful and useful method for finding things. Generally does pretty well as far as whenever we're trying to classify things into groups or to do some sort of prediction of a value over time. Skip over that. Multi-class logistic regression. Basically, idea is you're trying to come up with a way of both coming up with scores to turn them into probabilities of correctness, because we generally like probabilities and we're doing artificial intelligence, partly because we borrowed some stuff from the whole statistics people way back when. So you have a weight of a vector, a score, which is that time some sort of a weight, and then doing a prediction. Non-parametric models, some concepts and terms. Non-parametric cannot be expressed with a set of parameters. It requires instance-based or memory-based learning. Nearest neighbor models, often k-nearest neighbors, are based on distance between points or readings. The idea is to find the closest to each other. A kernel is a function with inputs of distances, especially maps the points to a high. It's essentially going to a higher dimensional space, and so that you can separate things that aren't separatable otherwise. Support vector machines is a class of models for supervised learning. SVMs create a maximum margin separator. That's the largest possible distance to example points. This is that part where that line has that separating has a width, and this allows you to come up with an essentially way of determining how good something you haven't seen before is being done, because you have essentially a line that you can then start thinking of in terms of probability. It allows us to separate things by going into higher dimensions and using this kernel trick to transform points to higher dimensions, and then you're able to essentially use a hyperplane to do the separation. You only really need examples to do the separation, so you don't need anything else beyond that. Ensemble learning, the basic idea is to combine together multiple models. So in general, more than one do better. And whenever we do that, there's various ways you have to come up with, well, what does the group say? They may do things like voting, averaging, or something more interesting. Your basic idea is to combine these base models into ensemble models. There's various other approaches that is how you do that. So bagging, random forest, stacking, and boosting are the ones you'll hear most often. Generally speaking, your aggregates, your ensemble models do better than a simple model, in part because they're able to be bigger, larger, and then specialize, and then have a means of deciding who is the model that is best at specialization. Regret is that even if you think you may know the right way, there may be something that causes a problem. You still make a mistake or something. And so regret is a measure of your total mistake cost, the difference between your expected reward, including your youthful suboptimality, and optimal expected rewards. Idea here is trying to minimize regret. It goes beyond learning to be optimal. It requires optimally learned learning to be optimal. So it's a bit of a challenge. And sometimes you may have a random exploration so that you're essentially doing some sort of seeing what's available to determine if perhaps you should exploit versus explore. And whenever you're developing machine learning systems, this is kind of a common way that things happen. You determine what you are trying to prove or disprove or determine, which is called problem formulation. We take it and then collect some data, keep track of where you got it from, provenance, so that you're able to later on be able to speak to the veracity of the data potentially. You oftentimes cleanse and correct your data as well. Then you're going to move into model selection and training. You want to keep an eye on false positives, use a confusion matrix to see what's going on. And then at some point, you're going to move over to trust, interpretability, and explainability. So you're also going to want to make sure you're using things like version control. Even though you're doing ML, think about ML ops. It'll be your friend. Also, as something to keep in mind, you want to keep track of your experiments using something like MLflow. And then lastly, operation, monitoring, maintenance. You want to get them deployed and running and then keep them that way. And so because of that, you'll be using oftentimes technologies related to traditional hosting of like web applications or whatever. As always, if you have questions, let me know. I look forward to hearing from you, and I look forward to speaking with you again in the future.